Hello everyone, can you hear me? Can you guys hear me?
Yes, Professor.
Okay. Let's get started. First of all, sorry that I have to deliver the class online again, and actually we will only go back to the classroom next Wednesday, not the coming Wednesday, because each member of my family is getting COVID one by one. We all have mild symptoms, but we are quarantined. So we're basically quarantined one by one. I have two kids, so things are complicated. They cannot go to school. And next Monday, I have to. I have a trip next Monday, so I cannot deliver the class Monday 5. Instead, I will deliver the class this Saturday maybe. So it will be online. So you don't have to attend the live class this week for next Monday's class. I will deliver it Saturday morning, I think. But you are welcome to join. I will send you guys a link before the class. Then some of you can join. If you cannot make it, then you just watch the video. Okay, sorry about that. So if everything, I hope everything can go back to more normal next Wednesday. What's going on? Okay. So today we will keep talking about ROP. This will be our last class on ROP. So how many of you solved the last challenge, the return to, the overflow return 4, 64-bit version, the ROP one? How many of you solved it? So Gaurav, Andrew, okay. Okay, Sanim is still getting a second fort. Okay, looks like some of you got it. Then we will have the office hour Wednesday. So if you don't know how to do it, join the Wednesday office hour, then we can debug there. So today we keep talking about ROP and also talk about how to defeat ROP. Actually, there have been some real-world deployment to defeat ROP. All the functions you see in this class, they all start with END32, END64, that instruction. And that instruction is actually there to defeat ROP. But that instruction is only available on new machines. For older CPUs, that instruction is just a NOP. So that's why you see all the functions with compiler has that one. So if you run that function, the program on an older CPU, the CPU will just treat that as a ROP, as a NOP. If on a new CPU, if you just get a computer this year, last year, in the last 3 years, then that instruction probably can help your program defeat ROP. Okay, so we were going to say one more example today for ROP. So this one, you are going to craft your ROP exploit. We're not going to do this in class, but I will explain to you what's going on here. So this one is the ROP2 I designed before. So let's try the 32-bit version for a change. So the goal of this one is still to retrieve the flag. So you still need to generate exploits that open the file and print out the file. Just we are using 32-bit version instead of a 64-bit version. So you need to change your previous exploit a little bit. So this is the vulnerable program. The program takes input from, oh, I will update it a little bit because right now it takes input from exploit file, but the exploit file is not writable to you. So I will change it to temp exploit. So it will open the file and read only 190 bytes from there. And there is a buffer 200 bytes. So you can say that you are not going to overwrite the buffer, okay? So you cannot overwrite the saved RBP or saved return address. You will not be able to overwrite that. However, what makes this program vulnerable is these lines. So I basically inject the vulnerability of it, okay? So the goal of this is to, the key is here, this instruction. So we are going to find out whatever you put into the buffer, then move the first 4 bytes of the buffer to the return address. So you will be able to overwrite the return address, but only once, okay? You're not going to overwrite the 4 bytes higher than the return address, the 8 bytes higher than return address, no. But from the last example, you say that is what required for you to do ROP. You have to control the stack. Here, you don't have the full control of the stack. You can only control 4 bytes. That's the first thing. Second is, there is another instruction to move the second 4 bytes of your input, the buffer. Whatever you put in buffer, the first 4 bytes, I will write it to return. The second 4 bytes, I will write it to AEX. You don't have to understand the syntax here, especially the assembly code here. You don't have to understand. You just need to understand those 2 things. The first 4 bytes of your input will go to return. The second 4 bytes of your input will go to EAX. Then you are going to construct a route chain to take control of the machine to get the flag. I will give you a little bit hint here. So what you are going to do is you are going to find a class of gadgets. Well, we call it stack pivot gadget. There are several of them, and I think you can easily find the first one, which is exchange RAX or EAX ESP return. You can easily find this one. So basically, what you're trying to do is you're not going to use the original. So the first return address, you can overwrite it to that gadget. Then after that gadget, you are going to, then the program will not use the original stack anymore. It will use your stack. You can specify anywhere as your stack. You can specify the buffer address as your stack. You can specify environment variable as your stack, but you need to know that address and put that in EAX. And that EAX will be, that will to EAX, then you can, that will be swapped into ESP or RSP. So that's the idea of it. So I gave you a template here. Just I gave you the first 2 items here. The first one is the address of this gadget. The second one is your new stack address. After that, you need to develop your own open file, close file, open file, printout file, those things, just to change from your 64-bit version. Okay, any questions so far?
Professor, in the
Yes.
template, what does that I signifies?
What is what?
I, capital I.
Oh, this I? Oh, I use I here because this is 32-bit. Previously, we're using Q, right? Q, that means each item is 8 bytes. Here, each item is 4 bytes. That's an integer. The less than sign, I believe it means it's little endian. I'm not a Python expert. Yeah, I think this one means little endian. If it's a greater sign, it means just a big endian. Yeah, that's endianness, this one. You can check the document, Python document too.
Okay, Professor.
Any other questions?
Professor, I didn't get this part of the first line, like exchange EAX to ESP. That actually like we are doing that to move the 4 bytes to return move the 4 bytes to EAX value. The second one, I didn't get that part.
So this one will not be well, this one is actually, so here you should put the address of the gadget, right?
Yes.
And this address will be moved to this piece of code here. This code snippet will copy this one to the return address on the stack. And
Okay, got
here,
yeah,
this thing will copy this thing, those 4 bytes to EAX.
Oh, okay, got
That's
it. Yeah, got it.
Okay. Okay, let's keep moving forward. So we talked about the history of ROP. It was the generalized version was published in CCS back in 2008. After that, people have tried to extend the ROP. So in ROP, we always end with an instruction RET, return, right? Then other people find out we do not really require that. We can also use other indirect branch instructions. For example, like call or return or jump can also be used to launch similar attacks. And those attacks are called the call-oriented programming or jump-oriented programming, COP or JOP. So in this class, we do not really talk about those two attacks, but if you are interested, you can Google to find out how they work. Very similar. Okay, next we talk about how we can defeat this class of attack, ROP, JOP, or COP. So like all other attacks, like the buffer overflow, format string we analyzed before, whenever you see an attack, you think about what are the elements to make this attack successful. If you list them, you list all of them, sometimes some of the requirements are just so natural, you do not realize that is a requirement, right? But if you can write them down, list them, and if you take them one by one out, then you can design all kinds of defenses. I'm not talking about the defenses are perfect. Some of them cannot really eradicate the problem, but they can make the attack much harder. So let's think about ROP here. So to pull off a ROP attack, as an attacker, what you need to do is you need to somehow control the control flow. You need to subvert the legit control flow and make the control flow to execute your first gadget. And usually after the first gadget, things are easy because you just put those items on the stack one by one, right? Second, you need to control the content on the stack. You do not need to inject code. This is different from the stack-based buffer overflow we saw at the beginning. You don't need to inject code, but you still need to inject data on the stack. Third, you have to rely on the program itself. There should be enough gadgets in the address space for you to use. Usually this is easy to achieve, especially on the system we are using. We're running on Linux system. Everything is a process, and the process uses a C library. So there are plenty of gadgets for you to use. But for some low-end devices with a very small address space, you probably cannot find enough gadgets. Four, you need to know the address of the gadgets. Remember on the stack, the items, many of those are just the gadget's address. If you don't know the address of the gadgets, then you cannot execute those gadgets, obviously. Also, the gadgets could be anywhere. The gadgets could be in the middle of a function. The gadgets could be in the middle of a legit instruction. So you should be able to start execution anywhere. So this is a requirement that is natural on most machines. Most machines you can return to anywhere. You can call anywhere at the hardware level, at the instruction set level. As there is a call instruction, you can call anywhere. There is a return instruction, the target can be anywhere, right? So this is a natural requirement. It sounds like very hard to take this out, but I will show you today some of the efforts that what they are trying to do is to take out this requirement. We do not allow execution from anywhere. Okay, that's basically it. So the first idea to defeat RobCop or any other approaches is something called control flow integrity. And this paper was published in CCS 2005. It's called, the title is super short, just the control flow integrity. The first author, Martin Abadi. So he was a professor. I think he is still a professor at UC Santa Cruz. He made a lot of contributions in a lot of different things, not only system security, also AI. He also works in Google. So he made a lot of contributions in artificial intelligence as well. So the idea of this paper is all the control flows when a program executes should stick to its allowed control flow graph. So so imagine in ROP or in buffer overflow, we're basically asking the program to run some code we inject. So the control flow goes to a place which should not be, sorry, my phone, should not be allowed there. So the idea of this paper is for any program to execute, wherever there is an indirect call or indirect jump, for example, a call instruction to a register, that's an indirect call, a jump instruction to a register, that's an indirect jump, or a return. A return is also kind of like an indirect jump. All those, the target should be, the valid target should be determined at a compiler time. And at runtime, we will check if the target is really a valid target. So then we can separate this into two different things. One is called the forward control integrity. Forward control is something like a call or a jump. Another thing is a backward control flow integrity, which is the return address, and which is return and return address. And we already saw that actually to defeat previous buffer overflow, we talked about a shadow stack. And the control flow integrity, shadow stack actually is part of the control flow integrity. Shadow stack takes care of the backward control flow. And the shadow stack was also first proposed in this paper. And here is the interesting thing. This paper was published in 2005. It was before ROP. Okay, ROP was 2008. So before ROP, people already come up with the idea that can defeat ROP. It's just that sometimes those ideas are very expensive, not very practical. Control flow integrity is a very expensive approach, expensive in analysis time and also expensive in runtime as well. Remember the shadow stack. I remember we said that for most of the programs, the shadow stack overhead is like 3%, 3 to 5%. That's the overhead. That's already quite high, and that only protects the backward control flow. Doesn't protect the forward control flow. Forward control flow is even more expensive. So if we can enforce CFI, it means we can take away the attacker's ability to subvert the control flow to their first gadget. So it will not work. So this is a approach, however, doesn't work. I will show you some CFI examples. Most compilers we're using now, some of them have some CFI extensions, but I tried the latest GCC. I didn't find yet actually. So I will only show you some examples from papers, not from actually code. My lab actually, we're also doing CFI, but we're doing CFI for a very low-end device. We change the compiler to enforce CFI on low-end device. We're using some hardware features to make this super fast. The paper we're going to submit soon, in those very low-end devices, our performance is 3% something for both forward and backward CFI. Yeah. So CFI restricts the control flow of a program to only valid execution traces. At runtime, it enforces this property by monitor the program and compare its state to a set of pre-computed valid states. If invalid states is detected, then an alert is raised. So this part is kind of like the stack cookies. So at runtime, that is each beginning of each function, it will insert a cookie to the stack. At the end of the function, it will compare that cookie with some secure copy of that cookie. That's basically the monitor. If the monitor find out the cookie have been changed, then it will generate an alert, something like stack smashing detected, then usually terminate the program, right? So for any CFI mechanism, it has two components. The first one is an offline, often static analysis component to generate a control flow graph of the application. And this part sounds simple, but it's actually very difficult because here we are focusing on the indirect calls, not the direct calls. I will show you more examples later. Also, there is another dynamic runtime enforcement module that just whenever you jump to somewhere, it compares that place. So this is like a stack cookies. You the compiler will insert some comparison there to say if the jump or call is valid. So I already talked about this a little bit. What is indirect call and what is a direct call? This is usually, we probably do not really cover this in any class, I guess. Even your assembly language class probably don't cover what is indirect, what is direct. Okay, so basically direct call, direct jump uses an instruction, use a call or jump instruction with a fixed address as argument. Fixed address means the target of that instruction is determined at compiler time. So well, not necessarily compiler time, also could be linking. Well, sometimes it's dynamic link, but it's the compiler and the linker will determine the address. So let's say if that's a piece of code and that there is a call instruction and the target of that call instruction is already fixed, then there is no reason at runtime you want that piece of code to be updated or changed, right? That's why the code section usually is executable, readable, but it's not writable. So this is different from the stack section, right? The stack section, we use DEP. The stack is writable, readable, but it's not executable. The code section is readable, executable, but not writable, okay? So if it's a direct call or jump, then it's pretty secure as long as we make the memory not writable. We don't need to protect it. No one can change the code. So no one can change where we jump to, where we call to, okay? What we really need to protect is those indirect jump or calls, including the return. Because the target is determined at a runtime. Only when you execute that instruction, you know where the target is. For example, there are indirect call instructions that call RAX or EAX or jump EAX, RAX. So only when you execute this instruction, the value of RAX will be your target. But that value, sometimes it's possible to find a set of possible values for that target, but sometimes it's impossible. What if the input is related to user input, right? You can write a program like that, but obviously you should not, because user input could be malicious. If you jump to a user input address, your program is obviously vulnerable. And also function return is also indirect because the target is on the stack, and everyone can write the stack, and the address is not hard coded in the instruction. Like I said that on the call or jump, they are named the forward edge, because if you draw a control flow, that will be one direction edge there. And return instruction is a backward edge because it goes back to the function that calls your function. Also, this can happen at the kernel level with interrupts and interrupt returns. By the way, one of our contributions in the paper we're submitting is our paper can also handle interrupts and interrupts returns. Okay, so here I give you one example. If you want to read more about this, this is a website. So this example was given by a professor from Purdue. He was a professor from Purdue. He did a lot of software security projects. Very famous guy, but recently he, I think he's European, so he went back to Europe. Right now he is a professor at I'm not sure it's ETH or EFPL, one of those two. Yeah, basically the best technology university in Europe. So he wrote this blog here, so you can read this. Let's say, how should we implement CFI here? Look at here. We define 4 functions. One is called bars, another one is bars, the third one is also bars. You see that those 3 bars, they have the same prototype, okay? Then there is another one called base. This one has a different prototype. It takes 2 integers as input. Now we have a function. The function, at the beginning of function, we define a function pointer. We define a func as a function pointer. Then we are going to set the function pointer based on some user input. The user here is a user input. Let's say if the user input is magic, we are going to set the func as bar. Otherwise, we set as bars. Okay. So as a human, when we look at this function, when I look at this code here, we know that there are 2 valid targets for func, right? Only 2. One is bar, another is bars. Everything else should not be valid target. So if at runtime, when we really call this function, okay? So here, then we've called this function. So if the compiler is smart enough, the compiler should check which function we are calling before we call this function. Also, before we return this, we should check the backward edge. So this one, let's do not discuss this one for now, because this one is more like this one we can use shadow stack, right? So let's say here, the forward edge. Before we make this function call using the function pointer, we should check if that function pointer is pointing to something valid, not pointed to anywhere in the memory space. Imagine there is a memory copy at the here. The memory copy can overflow the func C. Then we can then we can override function C to anywhere in the address space. But obviously that's not what we want. We wanted the function is only those two. Okay, this is not easy to achieve at the compiler level. That's why there are always some compromise. The first level of compromise is, let's say at the compiler level, we will insert some checks. This check will allow all function calls, as long as at runtime, this func C points to a valid function. We say this is okay. Or let's say, we say the func C has to return to a function with a specific prototype. For example, the first three, right? Or the best case, the best possible is we can do some very complicated program analysis, and the compiler can say for sure this function C pointer can only point to those two. Then at runtime, we only allow those two. However, in this example, it seems very easy to do that, right? But in real world, the programs are much, much more complicated. And sometimes it's not possible for the compiler to identify those taken functions. Sometimes just not possible. Any questions so far? Any questions regarding CFI? Okay, so remember, CFI is just when before you call this function, the compiler will insert some instructions to make sure the function you are calling is in a valid set. If it's not, it will just crash the program. Okay, the second approach to defeat ROP is another friend we are already very familiar with. It's ASLR. So the idea of ASLR is to randomize the location of different modules in the program. Of course, the idea can be even more fine-grained. You can even change the locations of functions, not necessarily modules. So technically, you can do more complicated program analysis to figure out whether instructions are related to each other, and you can even randomize the location of instructions a little bit. Well, this one depends on the interdependency between those instructions. Sometimes swap the location of the several doesn't really matter. So ASR makes it very difficult to do ROP because you don't know the address of the gadgets because they move around, right? However, this will still be a problem for some programs like web servers, because ASLR only happen when the server is loaded into memory. When the server fork itself to millions of copies, all of them will have the same address space. But I showed you guys a paper from NDSS before. Their idea is they are going to re-randomize addresses again at fork. So this is the second approach. The third approach to defeat ROP is, how about we just remove the gadgets? Remember, one of the requirements is there should be enough gadgets for us to do our malicious purpose. So what if we remove the gadgets? What if we recompile the C library? And the generated C library will not have many gadgets or no gadgets at all, right? That is the idea. So basically, you remember the gadgets need as a return instruction, which is just a C3, CB, C2, C8. So how about we compare the code and we do not have those bytes? You see, this is kind of similar to what you did for share-code, right? In share-code, in the ASCII share-code and the non-zero share-code, you were trying to find the equivalent instructions without those non-ASCII characters. Here, we are just trying to automate things. We do this at compiler level. We're going to compile your C code, but the generated C code will not have those bytes, those C3 bytes, C2 bytes. For example, let's say there is a jump instruction. So this jump, you can see, this is a direct jump. This is a direct jump instruction. This jump itself is not indirect. However, this jump will have a C3 here. You may find this is interesting. Why there is a C3? Because here we are jumping to C8. Okay, at the assembly level, what you are going to code is jump to the current place plus C8. Okay, but after you compare it, it will actually there will be a C3. The reason is the instruction itself is 4 bytes. So the instruction, it will code the target at the compared to the end of its location. So that's why after you compare it will be C3. But when you write the assembly code, you are thinking about the beginning of the instruction. So it's C8. Okay. So anyway, so when you compile this instruction, there will be a C3, and that C3 can be interpreted as return. So before this, there could be some gadgets, right? So the idea of this to get rid of the gadgets is very simple. Instead of a jump to C8, we're going to change to jump to C9. Then after that, there is 1 byte of lop. That's it. So if we can change to this equivalent code, we are removing the gadget. As simple as that. So sometimes I mean doing research is just so simple. Okay, it's not that difficult. So any of you can do this as long as you have the background knowledge. You can see there are many things you can do. Obviously, you can see these kind of ideas. They're not like super powerful ideas that solve the problem from the bottom. It's not. But those kind of approaches sometimes could be very practical in real world. This paper didn't go to the top 4 big conferences, but still go to a very good conference. XAC is also a very good conference, and they publish a lot of very practical papers as well. So those kind of ideas very easy for you to understand. I mean, no matter you are undergraduate student or graduate student, you can see it's not that hard. Let's say one more example. Say there's another instruction and the C2 to EAX. So there's a C2. Then just like what you did in your share code, which is just the changes to into instruction. We change it to add C1 and increase EAX. They are equivalent, but there will be no C2 anymore. Or this one, there is a CA. We compare this to C9, increase this, then do a XOR, right? Those are one more example here. So I took those examples directly from the paper. Let's see what this example is. So here, the instruction is move EBP minus 38, move 1 byte to AL. However, after you compare this, somehow there is a CA. I don't really know why there is a CA, but obviously there is a CA. And looks like that CA is somehow related to that 39 here. Oh, I think it's probably because CA plus 38 is FF or 0. Yeah, that's the complementary of CA. Because here we're looking for a negative number. See, okay, I think that's why. So to change this is also very simple. We just increase EBP a little bit. So now we're not doing 36 anymore. We are doing 37. So probably we're not getting CA anymore. We're getting C9, right? C9 will not be interpreted as a return. So C9 is safe. CA, CB is not safe. Then after that, we just decrease EBP. So we change this. So you see, so to remove gadgets, we can also secure this. So this approach would be a compiler. So far we've been talking about 3 different approaches. The first one is CFI. CFI is compile time and also runtime. Compile time, you have to change the compiler to find the legit control flow or as accurate as possible control flow. Runtime, you need to verify where you're jumping according to is a legit target. The second approach we talked about is ASLR. ASLR is totally runtime. You don't need to load, well, actually you also need a little bigger compiler time information. The third one is the remove gadget. And this approach is totally compiler time. You recompile your program, change it. Well, this technically can work at a binary or C code level. You can implement this as a compiler pass. Whenever you get a C code, you generate the secured version of C code which do not have return. Or give you a binary, then you directly do binary analysis and remove those CACB state 3. The fourth approach we're going to look at is called the monitor CFI. It's also part of CFI, but it's using some hardware approach. It's rely on some hardware approaches. This is quite similar to what we are doing, but we are doing on very low-end devices. They are working on a general device. So, for example, this paper, K-Bouncer. I don't remember where this paper is published. K-Bouncer. It's called Efficient and Transparent ROP Mitigation. The idea is a runtime detection of abnormal control flows, and using the features find in our new CPUs. So some of the new CPUs has a trace buffer, can record what programs, what instructions has been executed. So our goal is just we can examine that buffer, and in that buffer, we check whether the trace was valid. Did we call anything invalid there? And also, let's say a simple approach is we can just count how many return we have been executing recently. So in return-oriented programming, you already say that our gadgets usually are very small. The gadgets, so far, you probably haven't used any gadgets longer than 5 instructions, right? So there are only 3-4 valid instructions, then the return. So which means return happens very, very often. In 100 instructions, it's kind of like there are 25% or more are return instructions. That's not normal. If you write a normal program developed in C, your application, your C code will have a lot of instructions compiled. It will not have like 3 instructions and then a return, 3 instructions and return. So at runtime, we can monitor how many returns are there. If there are many returns higher than a threshold, we say probably there is a ROP attack going on. The last approach we are going to talk about is called the indirect branch tracking. And this is a defense you have all of you have seen at the beginning of the class, and we have been ignoring what this is. So remember, all the functions we have, they all start with this instruction, NBR32 or NBR64. And this is a 4-byte instruction at a 32-bit level. I'm not sure how many bytes it is at the 64-bit version. Probably higher. 8 bytes maybe. Yeah, we can check later. So in some new CPUs, they are called the CET CPUs. I don't remember what CET stands for. Control flow enforcement tracking, maybe something like that. So most of our, I believe most of you, your computers you are using right now have this feature. So this feature, those CPUs, when this feature is enabled, it means that when there is an indirect jump, indirect call or return, you can only, actually not return, this one doesn't care about return. This one only care about the forward. For indirect call or indirect jump, you can only jump to this instruction. You cannot jump to in the middle of the function. You cannot jump into the middle of the instruction. For example, if you jump to C, that work, program crash. You can only jump to this place. And the value of this is predetermined, which means the likelihood for you to have a gadget will be very, very small, because this thing is 4 bytes. You cannot have this 4 bytes happen to in your memory. Then after that, there is a gadget which you find useful. Very difficult, right? Does that make sense?
Professor, can you repeat this one again?
So some new CPUs, they have this feature called CET. When CET is enabled, whenever there is an indirect call or indirect jump instruction like this, like those instructions, like call RAX, jump RBX, those indirect call, indirect jump instruction, whenever there's an instruction like that, the hardware will make sure the target you jump to have this instruction, NBR32 or NBR64. If it's jumping to an instruction which is not this one, for example, you jump to the push, then the program will crash. That is a hardware feature. So the compiler doesn't have to do anything. You're not changing the program. You do not have a compiler injected a software monitor there. It's a hardware monitor to make sure you jump the target have this instruction. That's it. Is it clear now?
Yeah, Professor. But what if it is a wrapper function containing some system calls? Then we will be needing entire function to execute.
That's why every valid function will start with this. Every valid function will start with this. So you can say this is also kind of like a CFI, but not a very good CFI, right? But you can say this is a very inexpensive approach. First of all, it's hardware-based, super fast, and you also need to add one instruction or add 4 bytes at the beginning of all the functions. It's kind of like a CFI, but it's a very coarse grained CFI. It's like the func here. It's like the func, the target here can be any functions in your address space. But it cannot be in the middle of the function. It cannot be in the middle of any instruction. So it's not a perfect CFI. Look at this piece of code. The perfect CFI should be the func should only be allowed to jump to bar or bands. Only those two are allowed. We don't know which one, but those two are only those two are allowed. Anything, let's say the valid set has more addresses than those two addresses, then it's not a perfect CFI, but it can defeat some runtime attacks. And this is exactly our example. This is like any function you can call, you can jump to. But it's very hard for you to find the valid gadgets there. You can still do a return to libc, but you cannot do a fully functioning ROP. Make sense?
So in case if you want to execute the entire function, then it's fine, but we can't take the gadgets from the function. That's what you mean, right?
Yes.
Okay, got it.
Because let's say, here is a C3, right? So maybe this FF81C3, that could be a valid gadget. But you cannot directly return or jump to here because the CPU doesn't allow you to do that. The CPU will only allow you to jump to here.
But even if you jump to NBR, but at the end of the function, there's a return, right? We can somehow use that to return to some other.
But you are basically executing a full function. You're not executing just a piece of gadget. When you are executing a full function, I mean, it's probably not what you intend to do, right?
Yeah, I understand now.
Okay. That's all I have today, actually, for today. So starting from this Wednesday, we will talk about heap-based overflow. So we're going to hack malloc, free, those class of functions. We will spend 2 classes on that. Then after that, we'll spend 2 or 3 classes on something a little bit different. So far, we're talking about software security. We're talking about the instruction set architecture level. Yeah, we're using different instructions to build your share code or whatever. So we're in the last 3 classes, we'll move to a lower layer. We're going to talk about the micro architecture layer. We're going to talk about cache side channel attacks, and also the very infamous meltdown spectral attacks. You're going to do experiments to do meltdown spectral, simplified version of those. That probably will take another 3 classes. Then after that, we will have the final CTF. So that's basically the semester.
So how many homeworks do we have left?
Every week there will be a homework, so we still have 5 homework at least, I guess, 5, 6. And you need to check the syllabus. The syllabus says it's 14 homeworks, I believe. Why do you ask this question?
Oh no, I just wanted to know.
Yeah, I think there will be. So how many homework we had so far?
10.
10. Okay, I think no more than 14. I think it's 14. You need to check the syllabus. Yeah. It's also possible that I only prepared 13. I will need to check. If I prepare 13 and the syllabus says 14, then I will just give you guys 45 points for free. Yeah. Yeah. Okay, we have a short class today. Let's see. Looks like there's one more question. Are we done with raw plot? Yes. Yes, we're done with ROP. That's what we're going to talk about, ROP. Okay, seems there's no more questions. Then see you guys Wednesday. Remember, I have an office hour before the class. If you have questions about ROP and your homework, just join the office hour. Okay, see you. Bye.
Thanks, Professor. Bye.